In this video I will show how to dim a 0 to 10 volt dimmable ceiling light or a light strip from a browser using Node-RED running on a Raspberry Pi. Previously I explained how to set up Node-RED on your Raspberry Pi to control a small LED from a browser. This time we will extend that to switching and dimming a real light fixture. I will guide you step by step through this project. Here's a short preview of the end result of this project. Here you have the interface. It's actually on a web page, so you can open it on any device that's connected to the same network as your Raspberry Pi. And here you see the light panel that is controlled by the system. You can switch it on and you can dim. You see the reaction time is quite okay, and switch it off. I'll first explain what you will need for this project. Then I will provide a system overview of the hardware and the software. Then we'll go into detail for the hardware, the PWM to 0 to 10 volt converter and the main switch. And for the software I will first explain about the GPIO command line basics. Then we'll dive into the Node-RED flow program. When we have uploaded the software in the Raspberry Pi, we'll first check the software function just with some LEDs. And then we'll put the system together and do a full system demo. At last I will explain a bit about selecting your 0 to 10 volt dimmable LED driver. So what will you need for this project? First, a Raspberry Pi 3 or 0W with Node-RED and npm installed. I explained how to install that in a previous video and I will include that link in my comments. Then you will need a LED light fixture or LED light strip to dim with your web interface. A 0 to 10 volt dimmable LED driver, fit for your light strip or light fixture. It is of course more convenient just to directly buy a LED fixture or LED strip which is already 0 to 10 volt dimmable. Then you will need a Windows PC and a Wi-Fi router. This to connect to Node-RED programming environment and the Node-RED user interface. Then you will need some basic electronic tools, like a multimeter, a solder iron and a wire cutter. At last you will need some electronic components to make your PWM to 0 to 10 volt interface. I will include a list of materials in my comments. So now we have a 0 to 10 volt dimmable light fixture and a browser on a smartphone. How can we get them connected? Let's start at the 0 to 10 volt dimmable light fixture. First we will need a 0 to 10 volt signal and a main switch to dim and switch the light. For this we will build an electronic interface which converts the digital PWM signal to DC 0 to 10 volt and a digitally controlled main switch. Then we use the GPIOs of a Raspberry Pi to control the main switch and generate the PWM signal. On the Raspberry Pi we have Node-RED running with a user interface with a switch and a slider. The Raspberry Pi will connect to the local Wi-Fi network and broadcast that user interface to the IP address, adding port 1880/UI for user interface. Now any smartphone, tablet, iPhone or Windows PC that connects to the local network via the Wi-Fi router can access the user interface in a browser via the IP address at port 1880/UI. This is the schematic of the web to 0 to 10 volt interface. This electronic interface has four main parts: the PWM to 0 to 10 volt converter, a 5 volt supply for your Raspberry Pi, a main switch to switch on and off the light, and an indicator LED. Let's start with the most complex part, the PWM to 1 to 10 volt converter. The Raspberry Pi cannot create analog signals. Instead it has PWM outputs, which simulates an analog signal by switching on, off an output at very high frequency. If the GPIO is high for 10% of the time, the effective voltage will be 10% of 3.3 volt or 0.33 volt. At 50% of the time, the effective voltage will be half of 3.3 volt or 1.65 volt. The The low-pass filter built with R3 and C1 will smooth out the PWM switching. The filter frequency is 34 Hz, which can be calculated with this formula. The Raspberry Pi switches in the kHz range, so 34 Hz is sufficient. So now we can create an analog DC signal of 0 volt at 0% to 3.3 volt 100% from our Raspberry Pi. But we need 0 to 10 volt for the dim input. 3.3 volt is not enough. This we can solve with a non-inverting amplifier built with an LM358 op-amp. The amplification can be set with R1 and R2, and in this case it is set to 3.1 times. You can calculate it with this formula. This way we can get a voltage swing of 0 to 10.3 volt. The LM358 can work on a single voltage source and can get pretty close to 0 volt. Not all op-amps can do that. Please remember to ground the pins 5 and 6 of the second amplifier in the IC, otherwise the IC may start oscillating. Then there are R4 and R5. They provide an initial dim value of about 75%. When you power up your Raspberry Pi, it may take 1 to 2 minutes before your raw Node-RED program has started. At that time the PWM out on GPIO 13 is floating. This will result in a minimum dim level. R4 and R5 are a voltage divider providing about 2.5 volt to the input. Amplified times 3.1, that makes about 7.7 volt on the output. So your light will be at about 77% of the light output until your Raspberry Pi has fully booted up. You can set this initial level by adjusting the values of R4 and R5. The output of the LM358 can withstand a short circuit for some time, but be careful with it. I will include datasheets of all key components in the Datafile. You can find the link in my comments. Now let's have a look at the 5V power supply. The Raspberry Pi needs 5 volt. The 0 to 10 volt interface needs 12 volt. The 12 volt comes directly from a 12 volt adapter. The 5 volt is made with a LM317 voltage regulator. You can set the output voltage with R6 and R7 using the following formula. In this case, 1K and 330 ohm makes 5.04 volts. The LM317 is protected against overheating and short circuit. It is recommended to add a capacitor on both the input and the output for regulation stability. I will include the datasheet of the LM317 in the data file, of which you can find the link in my comments. The 5 volt here is directly connected to the Raspberry Pi's 5 volt pin of the GPIO. I do not use the micro USB input. This worked for me. Also some references on the internet confirmed it is okay for the Raspberry Pi Zero. It seems not recommended for the Pi 3 because there are fuses in between. Anyway, be careful, if you connect this 5 volt wrongly, you can destroy your Raspberry Pi. Then here's the main switch circuit. I used the 12 volt relay because they are more common and I had one lying around anyway. GPIO 27 drives the base of the BC547 via a 1K resistor. The base current is 3.3 volt minus the 0.6 you lose here, divided by 1K is 2.7 milliamps. With an amplification factor of 200, that's more enough to switch the relay. This diode is very important. When you switch off the relay, the energy in the coil will generate a high voltage spike that may fry your BC547. The diode will freewheel this energy through the choke until it's dissipated safely. Note that I use the break contact of the relay. This is to ensure that the light is on during boot up. As mentioned before, it takes 1 to 2 minutes for the Node-RED program to start after mains is switched on. The inversion, anyway, is easy to fix in the software. GPIO 0 means on and GPIO 1 means off. Then there is an LED connected to the GPIO 17. This one will be blinking, not only because blinking LEDs are cool, but also to have an indication that your Raspberry Pi is operating and the Node-RED program has started running. This is what the final hardware looks like. I built this full system on one PCB that fit an existing electronic casing. Here's the mains in and output, and here's the 0 to 10 volt output. Here on the left you see the Raspberry Pi, it's a 0W. The Pi Zero is very compact and cheap, just a bit slower than the Raspberry Pi 3B, but for this project it's just perfect. Then here's the Adam3 17 voltage regulator mounted on a heatsink. It will dissipate about 1.5 watts. So without a heatsink, the TO220 package has a thermal resistance of 50 degrees per watt, so it would reach about 100 to 125 degrees Celsius, which is still okay, but a bit hot, so I recommend to add a small heatsink. Then here's the Adam358 amplifier and the relay with the quenching diode next to it. And here's the blinking LED. This here is the 12 volt adapter. I took the PCB out of the casing and added it on the system PCB as a component. I actually do not recommend you to do so, because if you make any mistake, the mains voltage will be connected to your light fixture and you are liable as you opened the adapter's casing. For instance, if these GPIO wires flip over this side, you have a very dangerous situation. Anyway, you are working with high voltages and people do die from electric shocks, so please be careful. The great thing of the Raspberry Pi are the GPIOs, or the general purpose input-outputs. The GPIOs are the bridge from your software to the things you want to control with it. In total there are 26 GPIOs, some with special second functions. For instance, the GPIO 13 and 12, which can be set as a hardware PWM, which we will need to make the 0 to 10 volt dimming signal. You can control the GPIOs directly from the command line using the WirpingPi function, which comes with the Raspbian operating system. One remark, the GPIO numbering has some history. In WirpingPi you need to use the WPI numbers. Let's go to the Raspberry Pi so I can show how this works. We are now at the Raspberry Pi. Let's start with switching off and on an LED. First I open the terminal window. Make it a little bigger. So let's take GPIO 13 as an example. I connected an LED to GPIO 13, as you can see in the caption below. Let's first check the status of all GPIOs with the command GPIO read all. GPIO read all. Here you can see a table of all the GPIOs and its status. Now we configure GPIO 13 as an output with the command GPIO mode 23 out. As you see, I use the WPI numbers here because this is the WirpingPi tool. Now GPIO 13 is set as an output, and we can make it high with the following command: GPIO write 23 1. And you see the LED is on. And we can make it low again with GPIO write 23 0. And the LED is off. Let's check the GPIO status again with GPIO read all. And you see here the GPIO 13 is now set as an output. As mentioned, GPIO 12 and 13 are special and they can be configured as PWM output. Let's do that. GPIO mode 23 PWM. Now GPIO 13 is set as a PWM output. Now you can set a value between 0 and 1024 for the PWM. Let's try that. GPIO PWM 23. Let's set it to 1000. As you see, the LED is on and it's quite bright. Now we can dim it to 10% by typing GPIO PWM 23 100. And you see the LED is much more dim. The hardware PWM of GPIO 12 and 13 can generate a very stable PWM signal. but can only be accessed from the command line with this WirpingPi tool. Node-RED only provides software PWM, which cannot be used for dimming because of glitches caused by the interrupts of the operating system. These glitches cause visible flashing of your light. I tried that and it's really not useful. But no problem. In the next section I will explain how to call command line functions from Node-RED, so you can also use this stable hardware PWM signal from the Node-RED user interface. You can find more information about the WirpingPi on this web address. In this section I will explain the Node-RED flow program. This is what the interface looks like. To test the software, I connected two LEDs to the Pi. A red LED connected to the GPIO 17, which is the on-off switch, and the blue LED to the PWM output. If you switch the switch, the red LED will switch on and off. As you remember, it was reversed. If you move the slider, you can see you can dim the blue LED. You can connect to this user interface by connecting to the same network as the Raspberry Pi and then enter the IP address adding user interface, UI. So let's now go to the Node-RED programming environment so I can explain the Node-RED flow program. This is an inject node. It only triggers the exec node at boot up. So it injects a timestamp. When at boot up this timestamp is injected, this execution node will start. This execution node can execute command line functions. In this case it will execute GPIO mode 23 PWM, setting the GPIO 13 to PWM mode as if you would type it in a terminal on your Raspberry Pi. This is the slider from the dashboard nodes. To get this node you need to install npm and add it in Manage Palette. I explained it in the previous video. I will add the link in my comments. The slider range is set from 0 to 1024, so it will send this value to the next node. The next node is another execute node. It sets the PWM level with the command GPIO PWM 23. Here the append message payload is enabled, which means that here the value from the slider will be added at the end of the command. For instance, GPIO PWM 23 500 if the slider is set at 500. The Raspberry Pi will execute the command as if it was typed in a terminal. Then here's another inject node. It injects 750 at startup. So at startup your slider will be set at 750 or 75% of light output. This trigger node, called off timer, will set the switch to off if it did not receive any signal from the on-off switch or the dim slider for more than 4 hours. Note that the extend delay if new message arrives is ticked. You can change the waiting time to test it. You can also connect a GPIO input with a presence sensor to this node, so it will shut down after no presence is detected for a certain time. In this case, only the dim slider and the on-off switch are connected. This switch node is also from the dashboard nodes installed with npm. As you remember, I used the relay's breaking contact to make sure the light is on during the 1 to 2 minute boot time, so the on payload is set to 0 and the off payload is set to 1. Then there is this inject node. This inject node will send a 0 to switch on the light at startup. This GPIO node controls the relay. Here I use the standard Node-RED node to connect to the GPIO. As you see, the interface is graphical and it's very convenient to set up. I just select here GPIO 17. I set it as a digital output and I put the name GPIO 17 on-off. This is a function node. In a function node you can add JavaScript code. In this case the LED blinking function. A variable light is set to true. Here an interval is set to 400 milliseconds for the function blink. You can change the blink speed with this value. Then we enter the function blink. First it will check if light is true. If so, the message payload is set to 1 and light is set back to false. Then we go to the end and the 1 is sent out to the output, which switches on the LED. The next time, of course, light was false, it will go into this else part, message payload is set to 0, light is set back to true, and a 0 is sent out and the LED is switched off and we start all over again. To initialize the function, you need to send a message at startup. So this injection node will just send a 0 to make sure that this function will start. Then the LED is controlled with this GPIO node. It's very similar to the relay control node. So GPIO 27 is controlling the LED. It is set as a digital output. I connected the interface circuit and the light fixture. You can see the light panel here in the ceiling in the caption below. Let's switch it on and you see the light is on. Let's see the dimming performance. Slider down, go to the minimum. So you see the reaction time is actually not bad. So that works really okay, and it also works from any other device. If you type in the IP address of the Raspberry Pi, port 1880 and then add UI. In this section I will provide some information about LED driver selection. If you want to replace the existing fixed output LED driver in your light fixture with a dimmable 0 to 10 volt driver, you will need to know the LED voltage and current. To check this, you will need to open up the fixture and check it. You will find something like this. This is the LED driver. You can find quite some information on the label, but this information can be confusing. When you read the label, you can for instance find here the output current, 700 milliamps. And you can see the voltage range, 25 to 43 volt. There's another voltage mentioned here, which is 50 volt, but this is only related to the safety class. The best way to check what you need is just to take a multimeter and measure the LED voltage at the driver output. You can measure it in this case here at these wires, or you can measure it at the driver. To measure the current of the driver, you have to cut this wire and use a multimeter to measure the DC current. You will need to have a 0 to 10 volt dimmable driver with a voltage range that covers your LED voltage, and the current that is equal or less than the current what you measured. If you take slightly less current, you will have a bit less light. For instance, 700 milliamp measured here, you can use a 600 milliamp driver, but it will be not as bright as previously. Then there are 1 to 10 volt dimmable drivers and 0 to 10 volt dimmable drivers. Officially 0 to 10 volt must go to standby if the voltage goes below 1 volt. Anyway, both work for our system as you have a relay main switch in your interface. Then there are light strips or light tapes. Light strips or tapes are mostly driven with constant voltage, 12 volt. They are not current driven. The current limitation is actually here in some resistors inside the tape, or there is a small circuit inside. For your 1 to 10 volt dimmable driver, please check the output power. It should be more than enough for your light strip, and the output voltage, that it matches your light strip. As said, most light strips are 12 volt. There are also 230 volt or 120 volt light strips which can be directly connected to the mains. These are not dimmable. That was it for this video. I hope it was interesting for you. If you have any suggestion or any question, please leave a comment.